Good morning, students. Today we will start module 4, that is the last module. The first topic of this module is reflection of plane wave at normal incidence. Okay, here we will consider two reasons, reason 1 and reason 2, and this is the boundary between the two reasons. Okay, now for reason 1, the characteristic of this region is mu1, epsilon 1, eta 1, k1. And the characteristic of region 2 is mu2, epsilon 2, eta 2 and k2. Now you know these characteristics. Mu1 is permeability, epsilon 1 is permittivity, eta 1 is impedance and k1 is phase constant. K1 is phase constant, which we know as beta. Okay, and eta is intrinsic impedance. Okay, 1 1 1 for medium 1 and 2 2 2 for medium 2. Is it clear? Now we will consider one plane wave is incident normally on this boundary between the two regions. Okay, this is a plane wave which is incident at normally. Okay, the angle between this is 90 degrees. Okay, so what will happen? Its electric field it be E and magnetic field is HI. Let it be, since incident wave, so I am writing EI and HI. Some part of this wave will be transmitted in the region 2. Okay, now I am writing ET, electric and magnetic field transmitted, so T. Okay, and what will happen? Some part will reflect back, so I am calling it reflected wave. Reflected, so ER and HR. Okay, and the direction of propagation of the wave be plus Z direction. This is the direction of the propagation of the wave. This is the direction on which it is incident on this boundary. Some part is transmitted and some part reflects back to the negative Z direction. Okay, now we also know that electric, magnetic field and the direction of propagation are perpendicular to each other. Let us start with incident wave. Incident wave. The expression for incident electric field is EIO e to the power minus j k1z. Now z is the direction of propagation plus z direction, k1 is the phase constant, EIO let it be the amplitude. Okay, therefore HI, that is the magnetic field, will be equal to, can be written as HIO e to the power minus j k1z, similar to electric field. Okay, now eta, what we know, eta intrinsic impedance, this is equal to E by H. So from here H is equal to E by eta. So I can replace HI here. Instead of HIO I can write EIO divided by eta 1 because reason 1, e to the power minus j k1z. This is our equation 1. So this is for incident wave. Next we will consider transmitted wave. This is a transmitted wave. For transmitted I am writing ET. Similarly ETO e to the power minus jk2z and HT will be HTO e to the power minus jk2z. Now HTO again can be replaced by ETO by eta 2. Eta 2 because it is in region 2. Transmitted wave is in region 2. Okay. Now we have studied boundary conditions. So from boundary condition we know that at the boundary the tangential components of the electric field as well as magnetic field is same. Therefore HI is equal to HT. We have got the value of HI and HT. So from these two equations we can write like this. Okay. Next is reflected wave. We have done with incident and transmitted. Now reflected wave. About reflected wave, similarly we can write this way, but for magnetic field I have written negative. Why this is negative? And one more thing, here it is not negative because the reflected wave, as you can see, it is propagating in minus z direction. That is why this is plus. Okay, and this is minus because when the wave reflects back, then its magnetic field changes its direction. Okay, so this negative sign is there. Again, HRO is replaced by ERO by eta. So this is equation 3. Now again, for boundary conditions, we know at the boundary the tangential component of the electric and magnetic fields are same. So at the boundary, I can write for reason 1 incident wave and reflected wave is there, and for reason 2 only transmitted wave is there. Similarly, for magnetic field, I can write. Now I have got the value of EI, ER, ET in equation 1, 2 and 3. Now my work is to put here the corresponding values. Okay. Now for Z is equal to 0, if you put Z is equal to 0, this component will be 1. So this will become EIO by eta 1 minus ERO by eta 1 is equal to ETO by this. Okay, so I am just replacing O to simplify it and writing this way. Now what I want, we want a ratio between ER and EI. So we will replace ET. How? ET is equal to, as we can see, EI plus ER. So I will replace ET with EI plus ER. Okay, so what will you get? Just EI I will take common from here, so 1 by eta 1 minus 1 by eta 2, and here ER, so ER is equal to 1 by eta 2 plus 1 by eta 1. Therefore ER by ER is equal to eta 2 minus eta 1 by eta 2 plus eta 1. This quantity EI by ER is known as reflection coefficient, which we have already done in transmission lines. Big T, this is equal to ER by EI, that is reflected electric field divided by incident electric field. This ratio is called reflection coefficient. Similarly, if you find a ratio between transmitted field and incident field, that is called transmission coefficient, and you will get a value 2 eta 2 by eta 1 plus eta 2. Only thing is you have to find ET by EI. Okay. Thank you.